The recording has started, so let me share my screen. Okay, so just 1 minute. So from last class, we started discussing directly from the textbook. This is the textbook. Uh, I uploaded a lecture last night, so that I hopefully you have watched it. If even if you missed that video, it's not directly connected with today's lecture, but I'm advising you to watch that lecture also in weekend, because next week there will be your first class test will be on next week Friday, at the uh, tutorial session. Today there will be no tutorial session, and but from next class there will be tutorial sessions from next week. And in the first during the first tutorial session, that is the Friday next week, you will have your first class test. Also by next week I'll send you a complete schedule of your all the test date and time of all your test and quiz. Means there are two kind of tests, right? Class test and fast quiz. So for both type of quiz and test, I'll share a sheet of the complete schedule for the semester. But yes, the first test is on next Friday. Now, starting with this textbook, as I have said that when I'll teach from textbook, I'll not prepare slide every time. So this chapter one I have already explained in the video that I uploaded yesterday. So let us start from chapter two, which is called instructions. Can I zoom it a little bit? I think now it is visible to all. No clear. Is it clear now? Anyone please confirm my voice is clear? Okay. Okay. Thank you. Okay, so from today we'll start discussing about instruction set architecture. You can see this chapter is about ISA. So as I said, my recommendation is first watch my lecture, and after watching my lecture, immediately you read the section that I have discussed from the textbook. Don't delay it. First watch my lecture, and after watching my lecture, within the same day you open the textbook and read that particular section or read particular part that I have discussed in the class. And also sometime when I will discuss from textbook, sometime I'll mention that this particular section is not important, or this within this particular section you can skip this part. So this those things you have to make record. So you prepare a notebook and you maintain a record for this, or which part is important from this textbook, which part is not important. You have to maintain those record by yourself. I'll not repeat it again. Okay, so I think what is called instruction is already known to you. Computer understands some commands, and those commands are called instructions. If you want to perform some work, if you think that the computer should do some work for you, then you have to give this computer a set of instructions. Those instructions are called program, right? A set of instruction is called a program. So there are different kind of instruction set architectures possible. What is called instruction set architecture? Instruction set architecture means the processor, which instruction set ISA the processor understand. So most of the Intel processor understand x86 ISA. There are some other ISA called MIPS. Okay, and in this course we are discussing RISC-V ISA. So these all are called ISA. So most of the processor that available in market from Intel and AMD follows x86. Then why I think I have already mentioned that why we are going with RISC-V, because it's simple. It's a simple, not complicated. If we directly start understanding x86, it's a complicated ISA structure. So that's why we are going with RISC-V. MIPS and RISC-V are also almost similar. Even there are some other version of the same textbook available for MIPS. So, but we are following risk. There are two important point here. That's why we are following this risk version of textbook, because risk is open source. anyone can download the source code of RISC-V, and they can also do modify the ISA if they want to work on that on ISA. And the next point is it's simple. That's why we in this course will follow RISC-V. So now if I scroll this chapter, first in today's lecture we'll cover these three subsections: 2.1, 2.2, and 2.3 will cover. So throughout this book, at least in the initial chapters, when you will read the chapter, ignore those examples or ignore those points written for Java. So they in this book, to make the examples understandable, they use some examples from Java programming language. So if anything you get from related to Java, you can skip that part. It is not required. Without understanding the concept of Java, or without understanding this section that is written for Java, you will understand the remaining concept. It is not necessary. So you can ignore that part. Okay. Now we'll start with introduction. So in introduction, you can see the first they have mentioned what is called instruction set. Now I think if we go for a RISC-V, then RISC-V is the ISA that we are using, right? And RISC-V has multiple instructions. Suppose I1, I2, I3, all are, there are many instructions possible. Suppose I100, there are many instruction possibles in possible in RISC-V. So the combination, this combination is called the instruction set. Okay, so this is called instruction set. So here they say the word, if computer understand a language, or which language, suppose the program that we can write using this instruction is called assembly language. So if this is a language, then the words of this language are called instructions, and the vocabulary is called the instruction set. Why? Because if these, suppose RISC-V has only 100 instructions, so whatever program that you will write, you can use only this 100 instruction. By using this 100 instruction, you have to write your program. Maybe your program is a very huge software. Maybe this your program has 4,000 lines, suppose. So all 4,000 lines will be written using this 100 instructions only. That's why this is called instruction set, and the program that you will write with this instruction, that is called assembly language program. And there is a small difference between the language that computer understand and assembly language that I already explained. Basically, the assembly language program is need to compile, or need to convert into machine language, and that part is done by a assembler. So but I explained that the binary representation of a assembly language instruction and a machine instruction is straightforward, and it's not a complicated task. That's why most of the time we assume that the instruction set or the assembly language instruction is executing in computer, to make it simple. Okay, so in this section, when you start, you'll find some discussion about other ISA, what is MIPS, what is Intel x86 ISA, and when the history of these instruction set architectures, and when you can see the RISC-V started on 2010. So all this simple concept will be is written here. You can read those concepts only once. That will be enough for you. And after this, you will see a table here. So this table shows most of the important instructions of RISC-V ISA. So I'm skipping this table now. You can also skip this table at the beginning, because at this moment, if you try to understand the content of this table, then it will be difficult. One by one, in this chapter and the next two chapter, we will understand all the instructions available in RISC-V ISA. And after understanding it, then we'll again come back to this table and discuss this table. So at this moment, you can skip it. When you will read the chapter also at the beginning, you can skip this table. So we can directly start with operations of computer. So what is operations of computer? If you remember the initial diagram, I show you that processor has a arithmetic logic unit, right? ALU. So if you want to add two variables, then there, first of all, we need to move those values to the registers, and then from register, the arithmetic logic unit will perform the addition. So it means that all the operations, means all computers support arithmetic operation. Arithmetic operation means addition, multiplication, division, and some other operations like comparing, two register, they are greater than or less than, and also there are different types of operations possible in a computer. So how computer perform those operations? So how computer perform those operation? I think this part I have already explained, that arithmetic logic unit performs most of the operations. We will not go internal to arithmetic logic unit at this moment. So now, means how you can write a program. So suppose you want to do this: a e- equal to b plus c plus d plus e. You want to perform this operation in computer. So as a C programmer, you can write this statement like a equal to b plus c plus d plus e. Assume that all this a, b, c, d are variables. So I hope you know the what is called variables in C programming. So you can write a statement like this, and if you execute this program and see, then you will get the result also, assuming that all these variables have some values already assigned. But when you'll compile your code, C code, this code to assembly language, this code will be converted into means multiple number of instructions. One instruction is not enough. Why? Because most of the instructions in assembly. So as from now onwards, I'll only discuss about risk V. So in risk V, most of the instructions, they can perform only binary operation like this. They can only perform this: a equal to b plus c, or maybe b equal to c plus d. This type of operation is possible, where these are called operands: a, b, c. These are, you can also say them variables or operands. So only three operands are possible. So this is the restriction. Why these restrictions? To make the design simple. If you read here, you can find why this type of design. Because the first design principle is to simplicity favors the regularity. So to make the design or make the processor design simple, this is the requirement that one operation performs only all the operations are binary. So if you remember the arithmetic logic unit that I have explained, arithmetic logic unit, it has two input, right? If you remember, and I said one register value will be passed through this, another register value will be passed through this, and this arithmetic logic unit will perform either addition or some other arithmetic operation, and you'll get the value here. So you can see, you can relate this, the operation that is performing in this arithmetic logic unit are means binary operation. Binary operation means only only two operands b and c are executing here, and the result is storing in another operand. So this is the requirement. We have to understand this requirement. So if considering this requirement, how can computer will execute this statement that you have written in your C: a equal to b plus c. So let us try to write this here. Let me expand it a little bit. I'll try to write it here. Okay, so first I can write this: a equal to b plus c. Okay, then I'll write a equal to a plus d. Can you understand it? What I have written? First, I have written a equal to b plus c. The next statement I have written a equal to a plus d. So after this line, what is the final value? Up to this point, up to this line, I think b plus c plus d is done. Now a is storing b plus c plus d. Or let us consider some value here. Suppose a is 1, 2, 3, 4. These are the value. So final result should be 1 plus 2, 3, 3 plus 3, 6, 6 plus 4, 10. Final value of a should be 10. So now after the first line, the value of a is, after this line, the value of a will be 3, right? B plus c is 3. After the second line, the value of a will be, now what is the current value of a? The current value of a is 3. So current value of a is 3. 3 plus the value of d is 3. So 3 plus 3 is 6. Now the current value of a is 6. Now we'll go with third line. Third line, I'll write a equal to a plus e. So now what is the current value of a? In this, current value of a is 6. So 6 plus e, 6 plus 4. So 10. So after the third line, the value of a will be 10. So you can see that this long expression that you have written in C, this expression will be divided into multiple sub expression like this, where only one binary operation can be performed by each instructions. So normally your program will be written in this way. So try to understand this format, how I have converted this to this, that should be clear. Now this is not assembly language instructions, right? So assume that there is an assembly language instruction in risk B called add. So if I write add a b c, Meaning of this is add the content of b plus c and store it in a. So basically the meaning of this line is a equal to b plus c. Add the content of b plus c and store it in a. If this expression you can write in this format, add a comma b plus c. So you can also say this is the destination register and these are the two source registers or source variable. I have not mentioned anything about register here. Why? Because if when you read the book you will see that they did not mention anything about register initially, because they assume that whoever is reading this book first time, they know the concept of C. So they know the concept of variables and all. So what they did, they actually built up the story with only with the concept of variable, and then slowly they introduced the concept of register. So I'll also do the same thing here, though I have given you a idea what is called registers in my initial lectures, but here let us not use the term register initially. Let us use the term variable. So here a equal to b plus c, there are three variables here. So now you can write it like this is the destination variable a, and then these are the two source variable b and c here. You have to remember this term, what is called destination, what is called source. Now using this instruction, assume this is a risk v instruction. Using this instruction, can I write this program? This is because this is not written in assembly language. Try to write it here. I'll write it. Where to write? Let me expand it a little bit. I'll write it here. So first I'll write add a comma b comma c. This will represent the first line of here, this line, right? The second line I can write add again a comma d. I hope you are getting. This is the second line. The third line will be add a comma e. So this is the risk v representation of your C code. So ultimately, when you will write a code like this in your C program and you will compile it, then this will be your assembly language code. So what is this? If you are a computer science student, then you will also understand this, I think, in your third year, most probably, or fourth year. So there is a subject called compiler. So in this course, I'm just saying that if you write a C program and compile it, you will get the assembly language code. But what is compiler? For now, at this moment, it is a black box for you, right? You are giving instruction to compiler. Okay, this is my C program, convert it to assembly language code, and compiler is giving it for you. But how compiler is designed? What is compiler? What are the internal mechanism of compiler, right? So those will be discussed in a separate course called compiler design. I think it is in your BTech third year or most probably in fourth year. I don't know. I'm not sure. But when you'll understand, when you'll study compiler, you will realize this is called intermediate code or three address code. And from intermediate code, we'll generate assembly language. So for us, only important thing is the assembly language code. So you can see here the same thing they have also written. The same thing they've written, that if you have an instruction like a equal to b plus c plus d plus e, then how to convert it to assembly language code. This is how we can convert to a assembly language code, assuming that this instruction is available in RISC V ISA. Add a comma b comma c. Okay. Now I am let us go here. So this is the example. I am just explaining it. I'm assuming that you will read everything from book. Okay. So suppose this is a program written in C again for you, and you are the suppose there is no compiler and you have to convert it to assembly language by yourself. So how to convert it? Previously I said that you have only add instruction a comma b comma c. Add instruction is there. Now assume that sub instruction is also there in RISC V. So first instruction means a equal to b minus c, b plus c, and second instruction is saying a equal to b minus c. So assume that both add and sub instructions are in RISC V. So one by one, I'll explain all the instructions in this way so that you will understand it. So now if you both add and sub instructions are available, how can you convert this code to assembly? First, you will write here add a comma b comma c. Here b and c are the source variable, right? And a is the destination. You will add b plus c and store it in the destination a. And then you will write sub d comma a comma e. I hope you are getting. So this is the assembly language conversion of this C. So they have same thing. They have also written the same thing here. Okay, so I hope you are understanding it. You read the book, you will understand it more detail. So now let us go with some complex design. So this is a complex design. F equal to G plus H minus I plus J. So if you know the C programming better, so you know the ordering of execution. So yes, there are some parentheses, right? So there are two parts here, right? This is one part, and these two parts will be executed first. So up to within these two parts, suppose this when we'll execute this, let us consider this will store in T0, and we'll execute this, let us consider this will store in T1. So as I said, in risk V, or only binary operations are allowed, means only at max you can go for a G plus H, or two operands, right? You cannot go with three operands. So you have to divide this expression into some sub expression. Let us divide it into some sub expressions. So what I'll write, let me write here T0 equal to G plus H, and T1 equal to I plus J. And then I can write F equal to T0 minus T1. I hope you are getting it. So instead of writing the complex F equal to G plus H minus I plus J, I can also write this, right? I'm using two temporary variable here. T0 is G plus H, T1 is I plus J, and then F is T0 minus T1. Okay. Now let us try to write assembly language code for it. So assume that both add and sub instructions are available to you. So first I will write here add T0 G comma H. Then I will write add T1 I comma J, right? Then I will write add F, sorry, last one is not add, last one is a subtract operation, right? So I have to go for sub subtract. I have to store the destination in destination is F, and then T0 T1. So this is your final assembly code. We started from here. This is the intermediate one, and then this is the final assembly language code. So this is a complex one. So we'll design more complex expression into assembly language like this. So till now, my intention was you have to understand that what are the instruction available, and you have to use those instructions only, and based on those instructions you have to write. So if your ISA is risk B, first of all you have to understand what are the instructions available in risk B. That's why if you remember there was a table, right? Let me just go to the table again. If we see, this is a table. So in this table all the instructions are there. So you can now relate the first two instructions. See in the table, add and sub, these instructions are there in risk B. That's why we are using it. If any instruction is not in risk B, you cannot use, because risk B processor will not understand it. So this is how I can say this is the set of instruction. You have to only use these instructions to convert your program into assembly language program. Okay. The same thing they have written here. I am not explaining it because I have already explained it. You read this example, you will understand it. And as I said, you can ignore this, the concept that is written regarding Java and all. This is not very important for you. Now let us go with operands of computer and hardware. So when I have written this type of instruction like A equal to B plus C, I said assume that as either variable, or you can say them operands. Normally we also call them operands. So first I said variable, now I am using another term called operands. Every time I say operand, you have to remember this, that I am saying about this A, B, and C, this kind of thing, or variables. So when we go for a programming language like C programming language, or like a Java, then the upper operands are variables, like, and there is no limit of variable. You can use almost infinite number of variables, right? There is no limitation. But when you go for a hardware programming language like risk V, which is understandable by a hardware, so in that case the variables or the operands has limitation. You cannot go for infinite variables. So what is the operands here in hardware? Operands are called registers. So I explained what is called register at the beginning. Registers are the fast memory units stored inside the CPU, right? You remember the example where I explained that you have to move data from memory to register first, and from register you can perform the arithmetic operation in arithmetic logic unit. So the number of, since your processor is a physical design, right? It's not a program, it's a physical design. So here the number of registers are fixed. You cannot, after a processor has been designed, you cannot change the number of register from 15 to 18. It's not possible. Number of register is fixed for the lifetime of that processor. So in the RISC V ISA, we normally RISC V ISA consider 32 registers. So if you go back to the table, I'm not going back to the table, that in that table, the topmost portion, they have mentioned that there are 32 registers in RISC-V architecture, and the registers are mentioned by X0, X1 to X32, X31, sorry. These are the 32 registers. So if you remember at the initial lectures, I have used this type of register like $1, $2, $3. So I will not use this type of register anymore. Normally these terms are used for MIPS ISA. So let us not use $1, $2, $3. Instead of this, we'll use X1, X2, X3, X0, these registers, because these are the 32 registers available in RISC-V. 32 registers, and size of each register is 64 bits. I hope you are understanding what is 64 bits. 64 bit means 8 bytes. You have to understand 64 bits means 8 bytes. So the size of each register is 64 bits here. And if you remember, when I was discussing the cache memory, I said this is your core, and if this is your cache memory and this is your main memory, then if core is requesting for a word A, then instead of getting one word, we normally move the complete block from main memory to cache. That I have explained, right? So, and that time I said the core request for a word, and I said the word size is normally 4 byte. Right, the word size is normally 4 byte, but the RISC-V design that will follow in this course will consider that the core is requesting for a double word, not a word. So you have to remember this. See, it is written here. The core is requesting for a double word. So double word means double of a word, means not 4 byte, 8 bytes. So every time core will request for this type of request, then it will not request for a word. It will request for a double word, that is 8 byte. So that's why 8 byte is actually 64 bits. That's why the size of each register is 64 bit. Every time it will request for a data, it will fetch and it can store it in a register. That's why each register size is 64 bits. Okay. So this small point you have to remember for the entire course. First point that I'm saying here, RISC-V design has 32 registers, X0 to X31. Each register can store 64 bits. This is the first point. Second point, I'm saying that core is requesting for a double word every time. Here we're assuming this. So core is requesting for 60 bit of data every time. Okay. But the concept that I have discussed previously was about was a word, right? And word means 32 bits. So it's not like that. It's not like that. Whatever I mentioned previously was incorrect. You can see a 32-bit design is also possible. Another popular size is a group of 32 bits called a word in RISC-V architecture. So that whatever I explained, that design is also possible. But here in this book, we are not considering this design. We are considering a 64-bit version. So there are the definition is here for double word, and what you must understand and remember these definitions. I may ask this. So one important, but every time you find this type of definition written in any chapter of this book, try to understand those definitions. Okay, so most of the concept is I have discussed. So yeah, one question: why number of register is restricted? You can see 32 register is very less, right? Because if we consider what I said, that operands are called register in hardware programming language, right? The operands I have written like this: A equal to B plus C. These operands are, when you will write a C program, there is almost infinite number of variables you can use. But why only 32 registers we can use in hardware? The concept is smaller is faster. If you use less number of registers, then the first point is the space required in your chip. Suppose this is your chip area, right? So the number of register you can store here, it will take some area of this. So hardware cost will increase if you increase number of registers, and also if you increase the number of registers, other hardware complexity will be there. So to make it simple, the number of register in a processor should be less. So that's why here we are assuming as where a RISC-V consider the number of register as 32. That point is very important. You have to remember it. With all this assumption, now let us go to the same program again, but now we will add some more concept here. Previously we just explained in terms of variable, and I said that just consider that a b this g h I j are variables. Here we'll add something more. When you will write a program like this in C, and you compile this program, then the compiler will convert your code to assembly. So when compiler will convert your code to assembly, then it is the duty of compiler to assign this variable with some registers, because here when you are writing a program in C, the variables, the operands are called variable, but when you convert it to assembly, the operands are registered. So there should be some mechanism who will assign your variables of C program to a registers of assembly language. So that is the job of compiler. So now, as consider that how compiler is assigning x19 to f, then this is to g, this is h, I, and j. As I said, when you compile your code, so how compiler is assigning? So compiler is assigning register 19 to f, register 20 to g, register 21 to h, 22 to j, I, and register 23 to j. So what is this x19 x20 wala thing? These are the registers of risk v that I've already mentioned, right? There are 32 registers. Out of these 32, I'm assigning these register to this variable fi, not me, compiler has assigned, suppose. So in that case, how your assembly language will look like? Here let us replace those variable and try to use registers. So first I'll write here add. I need to use two temporary registers also. Suppose I'm using, so let us not write it, they have already written, so I'll explain it from here. Concentrate on the first instruction. Add x5, x20, and x21. What is x20? X20 is g. So this line is doing actually g plus h. Okay, and where it is storing? It is storing in x5. So what is x5? X5 is a temporary variable. So you can say that some two more variables are required, right? T0 and T1, if you remember. So T1 they are assigning to x5, and sorry, T0 is assigned to x5, and maybe T1 is assigned to x6. So first line is actually T0 equal to g plus h. Second line is T1 equal to I plus j. How can we do it? So you can write, see, T1 is x6, so add x6, x22, and x23. So after these two lines, T0 and T1 are now stored in x5 and x6. Now I need to go for the final operation, that is subtract. Subtract means what to write? Here I need to write f equal to T0 minus T1. So f is actually x19, and T0 is x5, and it is x6. So I have to write sub x19 comma x5 comma x6, sub x19 comma x5 comma x6. So now this example is converted to the RISC-V assembly language code here. So what are the difference? The same program I have also written previously, right? But at that time there was some assumption. I have just used A, B, C, D that time. So those are not the registers. So now slowly what we are doing, we are trying to write assembly language which is the exact assembly language code of RISC-V. So if I scroll up and I'll show you, I have written the same program for you here also, right? Here also. But see, this is not actually the exact RISC-V. Exact RISC-V may T0, G, H, this type of things are not there. In exact RISC-V, they are actually registers. So this is why we use, as I said, this chapter is written in such a way that we are the chapter is moving towards from a C program to assembly language step by step, so that it will be easy for you to understand. That's why when I explain this part here, I have not mentioned anything about registers. Now let us introduce registers. So the same program I have written here with the introduction of registers. Okay, so I hope this part is clear. So after this there is so let us remove all this thing. If you have any question, you can ask. If any point that I'm discussing here is not clear, you can ask now also. Okay, there is a question here. Register assigned to operand are sequentially. Uh, can you explain it? I'm not getting your question, Mohit.
Sir, as
Talk
uh,
also.
it is mentioned that the
Let
register,
my speaker is off. Just 1 minute. Ha, Mohit.
sir, as it is mentioned that the X19 is assigned to F,
Huh.
X20 and X21, it should be sequentially or it can be randomly.
It there is no sequence here. It is random because see next point I'll discuss here, because see your number of registers are very limited, so it is never say it is not sequential, it is random, and compiler will assign it the register which are available, that register will be assigned by compiler. It is not sequential. Okay, Gautam, how does the compiler decide which register to overwrite if no register required is no the number of register required is more than 30? Gautam, I'll discuss this point now. So the next section is about your question. So how are the temporary register decided? Temporary register decided. Okay, suppose you are the compiler and you want to convert this code to C to a assembly language code. So you know that only binary operations are allowed. So you have to divide it into two temporary variables, right? So and I have given this name as T0 and T1. So T0 I said you will write G plus H, T1 you will write I plus J. So there is a logic right here. You have in your mind you thought something, and based on this you have used this type of temporal logic. Now first you have to divide G plus H into T0, and then you have to calculate I plus J into T1. The same logic will be applied in compiler. I cannot explain it in more detail because two more subject is required to understand all this concept. One is called automata processing, and then we'll go with compiler. Without knowing these two subjects, it will be difficult now to explain how compiler go with the temporary variables. So if you are from a CSA background, CSE, then obviously it will be clear in your BTech degree. But at this moment, how compiler decide this temporary variable, this is difficult to explain. So now if you are understanding that somehow you will go with this temporary variable, then this is enough. Okay. So now the next question of Gautam is now we will discuss this point here. So as I said, the number of registers are only 32 in RISC V. But if you write a C program, even if it is a small C program like matrix multiplication or comparing of two matrix or something, then also the number of variables can be more than 32. So how only 32 register can be used? Because in the previous example, here also you can see it is written that it is the compiler's job to associate program variable with register. But how it is possible when program variables are more than 32? How can compiler associate them with registers? So the question here, the answer here is registers are used only for the most important variables. It's not possible to assign all the variables to the register. It may be possible that initially when your program start, not a single variable is assigned to the register. So what is the solution? Solution here is von Neumann architecture. So at the beginning I said that initially your data and instructions are stored in memory, and one by one whatever is required we fetch it to the CPU and perform the operation. So if your program is huge and there are many variables are there, so compiler will do, compiler will assign all the variables in memory only. They will not assign those variable directly in registers. So if I discuss about C program, if I write integer a b, then these are the two integer type variables, right? So what we understand from that course, we understand that the moment we write integer a b, two variables a and b will be assigned in memory. जो memory होगा computer का, in this memory there will be 4 bytes will be reserved for a, and then be another 4 byte, may not be one after another. Next these 4 bytes will be reserved for b. So whenever we write integer a b variables, they are actually assigned a memory. So but in that course we never said what memory. Register is also a memory, right? Because we are storing data in it, means memory. So what compiler will do, If your program has limited number of variable, or compiler will check that which variables are most important, those variables will be allocated to register memory. Other variables will be allocated to the actual memory, means you can say main memory. Okay, so now I will explain it in upper level first. Since I have some time, I'll let me complete it. Suppose you have g plus h plus I plus j plus there are 5 variables here, but assume that you have space for only 3 variables. You can only use 3 registers. So what you can do, suppose initially f, g, h are in registers, and I and j are in memory. So how to perform this operation? First, you will perform g plus h. That is, this is available in register. But what is not available in register, what is in memory, what to do? First of all, we have to fetch those values from memory to CPU, right? And then we can perform the operation. Otherwise, it's not possible. So let us write a small code here. Then maybe that code will clear your doubts. So let me assume that all these variables are in memory. G is in a memory location 2000, H is in memory location 2008, and I is in memory location 2016, and J is in memory location 2024. All are when compiler assign everything on memory. Now how, and you can consider that out of all the registers, you are allowed to use only 2 registers. X20 and X21 is assigned to you. Other register you cannot use, because I assume that it's there, some other registers are using by some other programs, or there are some restrictions. Assume you can only use these 2 registers to perform this to convert this code into assembly language. So how you will do it? I assume that there is one more register you can use, that is storing the base address x1 equal to 2000. So first what you will do, you will load x20 में first of all you will load g. So suppose I'll write x1. So what is 0x1? 0x1 means 0 plus 2000, because I said the value of 2000 is stored in x1. The value of 2000 stored in 0 plus x1 means first of all you will go to memory location 2000 and fetch the data. What is stored in 2000? G is stored in 2000. So first you will go to 2000 and fetch G and store it in x20. So x20 is now assigned with G. Next, again, you'll go for a load instruction. Load here is LD. So previously I said LW, but here in disk B, load is LD. So now I'll use X21 to store 8x1. 8 comma x1, 8 plus x1 means 2008. So here I'm saying go to memory location 2008 and fetch the data and store it in x21. इसका मतलब क्या है? X21 में I'll store now h. So you can see now the variable g is now in x20, variable h is now in x21. Now perform a addition. Addition is like this: x20 equal to x20 comma x21. इसका मतलब क्या है? Somehow I'm writing this g equal to g plus h. That is also correct, right? Instead of going for t1, t0, I'm saying add g plus h and store it in g only. The same thing I've written here. Add x20 comma x20 comma x22. X21. So after this line, the result is now stored in x0. X21 में कुछ नहीं है, because this G is only storing this temporary result, right? So only temporary result is stored in G only. So let us go with X. Let us go and load now I. So what I will do now? No, थोड़ा change करना पड़ेगा, I think, to perform this operation. No, it will yeah, to make it simple, I'm going with plus, otherwise it will be complicated. So it is g plus h plus I plus j, suppose. So next what I'll load here, I'll load in x21, I'll load 16x1. Of 16x1 means what? 16x1 means I 2016. So I'm going to memory and loading the content of I and storing it in x21 again. So x21 may first of previously it was assigning h, now I'll override it with I. No problem, because the temporary result is stored in G or x20. Now I'll again write add x20 comma x20 comma x21. After this line, what will happen? G is now G. I'm saying G equal to G plus I, and G is currently G plus H. So ultimately, after this line, what I am actually doing is G equal to G plus h plus I. Up to this part is done. Again, I'll go to load and x21 फिर से खाली है. x21 I'll load 24 x1. Okay, and then I'll again go for add x20, the same thing I'll repeat. So after, in this way, you can see by only using three register, in fact one register to store the base address and other two registers, by three registers I can perform this complete operation. Even if there is a -1 minus here, that also it is possible. So why I'm making it plus, because to make it make the example simple. This example is not written in book, but you can see. So mainly when your number of registers are less, that's not a problem because we have a huge memory. So we'll store everything in memory. Compiler will store everything in memory, and whenever what is required from memory will be fetched, will perform the operation. And so at the last, suppose this was the case. Now f equal to this. So what is the this equation here? If we concentrate on this equation, is what is in right side, we have to perform those addition, and after getting the result, we have to store it in f. F is again a variable, and assume that f is in memory also. So suppose f is in 2032, suppose. So up to this what we have done, we have calculated the result, right? But the result is still in processor. A result is stored in still in x20 register. So if in this moment, if you just shut down your computer, then the result is not written in memory. So which instruction is required to write the result back to memory? That is called store instruction, right? So you have to write a store instruction that is called SD. Which register value we need to store? X20, because x20 is storing the current result. Where to store? We have to store in 2032. So we'll write 32x1. Once you execute this instruction, then your final value is be written back to the memory. So now let us go to the table again. Now you will see once you reach the table, you will see there are load and store instruction also. Data transfer mein jao, dekho, load instructions, store instructions are there. So in this way, you will try to relate the instruction that you are understanding. You will see those instructions are available in this table. That's why I said initially, you can skip this table, one by one, you'll understand it. So I hope you are getting that what is the importance of memory, and the same thing is written here, memory operands. This complete concept that I have explained, they've also explained here. Data transfer instruction means load and store. The purpose of load and store is clear to you now. You please try to understand these definitions. Don't just memorize any definition or anything. You have to understand it also. After understanding, it is good to memorize some important definitions, but first you have to understand it. Without understanding, do not memorize anything. And the diagram that is shown here, the same diagram I have also used already in my course to explain. This is the CPU and this is the memory, how initially everything in memory, and one by one how we need to move from CPU memory to CPU. That I've already explained, so I'm skipping this part. Lastly, you can see the here there is one more example how to convert this into C program. So what they said, this A8 you can consider is the array, right? You know the concept of array. So they are assuming it's the array. So every array has a base address. So assume that the base address of this array is stored in x22 register. They are assuming it. The base address of this array is already stored in x22 register. And now I think register G is assigned with A9. So let me write my own code here. So first of all, if you convert this to C, see, we have to move this content from memory to register. So load, maybe I'll also use x9 8 x22, because x22 is the base, and if it is A0, then A8 will be somewhere here. So this is how we can access the 8 element of the array. So the 8 element of the array is now in register x9. So if that case, if you assume that h is already in a register, suppose h is in 21 x21. So and suppose we assign x20, g will be assigned to x20. So what we'll write here, add x20 comma x21 comma x9. So if you write this line, then first you are moving data from this array to a register called 9, and then A8 is available in 9, a register 9, and then we are assuming that x21 is already assigned to variable h and x20 is assigned to g. So you can write this, add this line. Okay, but here one important point, as I said, that initially in risk B, we assume that every word is a double word. So we are also assuming that every array element is a double word, means it take 8 byte. So here, if you write 8 comma x22, that is not correct actually. If you want to access 8th element of the array, each element is taking 8 byte here. So instead of writing 8, you should write here 8 cross 8, 64. If you write here 8, that is actually not correct. If you want to access 8th element, you should write here 64. So here you can see that first they have used 8 here, they have used 8 here, and then whatever concept that I said about double byte and all, they explain it here in this section, in this section. And after this, they have rewrite the program here. They rewrite the program here with 64. I think they have not written the program, but they have mentioned it that it should be 64. So first they have explained it, the 8 element, they written 8, but 8 is not correct. It should be 8 cross 8, 64. So you have to remember, if sometime in your class test or exam, if I also give you this type of code and I say write the corresponding assembly language code, then you have to understand that to access a means ith element, you cannot write I, you have to write I cross 8. Okay, so up to this point is clear. I think please read up to this point. Try to convert this. If you convert this, you can see this part I have already explained, but this part needs some more changes. What? Because here the A12 is also a memory, right? So A12 is memory means first of all you have to load this memory into a register, and then you have to write the register, and again you have to you can store it, right? So first, suppose your this part is now stored in x20. This is the value stored in x20, but that is not enough because you have to store it in A12. So A12 में store करने के लिए you have to go for SD, then x20, and then 8 into 12, 96, x1. You have to go with this. I think they have written it here. See, they have used their store instruction. So load store is clear, add subsection is clear. So I'll stop here. Next class I'll start with constant and immediate operation. So my advice is please read the book, read the textbook, and if anything is not clear even after reading the textbook, then let me know. Don't just read those highlighted ones are for me. For when you read the book, you read everything, and only you leave those examples were written for Java. And even after this, if any point is not clear, then you can always ask me. Any other questions now? Yeah, Dilip, give me your email ID. I'll give it to you. I cannot share it because I don't know. Maybe there will be some copyright issues or not. I'm not very sure. So I'll send it to you. Maybe you can post or you can share. Okay. Yeah. Though the book that is available, I'm using is available in internet. I have downloaded from internet, but still I don't know. Maybe there will be some copyright issues, so I'm not sharing it. I'll send one of you, and maybe you can share it. And if there is no other question, let me stop the recording now. Stop presentation. Stop recording.